Hi everyone, my name is Malachy and welcome to Bite-Sized Temporary Works. In today's video we're going to talk to you about bridge maintenance temporary access. Bite-Sized Temporary Works' aim is to produce learning videos for the design and management of temporary works. So the aim of these videos are to provide you tips, best practice for the design of your temporary works, and you should always seek the advice of a competent engineer. In today's episode, we're going to look at the history of access to bridges, how people have accessed bridges over the centuries. We're going to look at some accident statistics from 1975 on the number of deaths in the construction industry as a whole, but particularly on bridge maintenance. We're going to look at more modern access methods. We'll briefly revisit the accident statistics then to see how these modern access methods have benefited temporary works. And then we'll look at some examples of platform loading and the different codes that are involved in it. So what is access engineering? Access engineering is putting operatives in a safe location where they need to complete their work. On many projects, bridges underneath jetties and harbours that need concrete or steel repair, the challenging part of the project is providing the access. The actual repair works are a smaller percentage of the project. So the main title for access engineering is the provision of a working platform that is suspended at intervals from a structure to allow a safe place for operatives to carry out a process to the structure such as construction, refurbishment or maintenance. And I like to simplify that and call it providing a safe place for people to work from. So we look at different types of access through the years, and one of the original access systems is the boatswain's chair, or as it's known in the shipping industry, the boatswain's chair. So there's an image here of the Fort Rail Bridge, and I'll just go on a quick tangent because that's what I typically do. An interesting fact about the Fort Rail Bridge is that on one side of the bridge, between the two sides of the bridge, the paint is thicker on one side of the bridge than on the other. And the side of the bridge that the paint was thicker on, which was the leeward side of the bridge, and what I mean by that was the shelter side of it. So over the years, when these operatives are working on the bridge and painting it, on a wet, rainy, windy day, which you do get a lot in Scotland, they would go to the sheltered side of the bridge and paint that. So in some cases, the paint is far thicker on one side of the bridge than the other. And that was the old lead paint systems. Since then, all that paint has been removed and there's a new modern painting system been put on it. But that is an interesting fact on the bridge. So the boatswain's chair or boatswain's chair is essentially a timber plank with 4 holes in each corner. It's bridled up to one central point, and then that's suspended off of a rope. You can see an image of it here from the shipbuilding, ship maintenance industry, where we have a mast and we've got a gentleman or operative who's sitting on this. So highly dangerous. Lots of accidents and deaths happened in these over the years. And with the introduction of the Health and Safety at Work Act in 1974, a lot of this working method was removed from the bridge maintenance sector, especially the Fort Rail Bridge, where they don't use this system anymore. The next system we're going to look at is a pickboard. So a pickboard, to describe it, if you see the arrow here in the image, the red arrow, you essentially have a horizontal tension cable between 2 points, and on this cable you put a bridle or a stirrup that hangs down like a U, and from that stirrup you can insert the pickboard through it. And a pickboard is almost like a ladder that you've laid on the flat with a sheet of plywood on the top of it. It's nothing more specific than that. And what the operatives do, when you see in the picture, the other picture, you can see an operative in a white suit, and they shuffle along this board to complete the maintenance works on the bridge above. So this could have been painting, it could have been repair works, it could have been blasting. They shuffle along from either end, and then when they're finished a section, they go to either end and they pull the stirrup along the tension cable. So these systems were prone to rotation. They were very dangerous. There was no edge protection in any way, and there was lots of deaths in these systems. So not an ideal system to use, but it was a historic system. Next thing I'm going to speak about is a catenary scaffold. There are many different forms of this throughout the years. It originated from the US Army Guide in 1926, and I'd probably describe it as a continuous pickboard. So you still have 2 horizontal tension cables, as you can see in the image here, but these cables are picked up at intervals by drop cables or vertical pickups. These vertical pickups are spaced at about a meter, meter and a half or so, not much more than that. And between these horizontal tension cables, you lay a board. This system is still used today, and there are more modern versions of it. And it's quite flexible, but it serves a purpose and it has been used for years and years. Scaffold, what can I say about scaffold? It is the default access system on bridges and has been for hundreds and hundreds of years. The pictures here on this are the Fort Rail Bridge, where being under construction, where you can see different types of scaffold used on it, mainly made in timber for accessing the works, and also the Clifton Suspension Bridge, and you can see some images here of old style type timber scaffolds. The scaffolds have been made from timber, bamboo, steel, and more modern access systems are made from aluminium. I'm not going to go into massive detail in this section because it overlaps with some other areas, but drop scaffolds, which are scaffolds that are used underneath bridges, are still used to this day. So hopefully that's given you an overview of the different types of systems that have been used over the years. They're the ones that I am familiar with. There will be other ones there that I haven't discussed. And when using these old historical type systems, what were the accident rates like? So you can see from this graph that back in 1975, there were 21 deaths per 100 million man hours worked in the coal mining industry, and that was followed closely by the bridge maintenance industry with 18.5 deaths. So a lot of work was needed, and there was an onus on increasing safety in the sector or the construction industry throughout, and the Health and Safety at Work Act of 1974 was one of the starting points for this. So we will revisit safety stats for 2018 later in the presentation. Now I'm going to speak about modern access systems. These are the access systems that I've been familiar with in my career. There are other access systems available, and I'm just going to go through these in detail over the coming slides. The first system I'm going to talk about, and you'll be familiar with it already from the presentation, is a catenary scaffold. Yes, it's a system that is still used today. It's a lightweight system, but it is very flexible to impose loads. So you can see for the image here, it gives you a large working area, which is relatively free of clashes apart from the cables and chains that support it. So the images on the top of your screen are access to bridges with a standard catenary system that has vertical drop cables at 1.5 approximately meters centers. And these brackets are then fixed to the underside of the bridge, the concrete bridge. What you need to take onus of here is that you are fixing into something that needs repairing. That's the reason you're there in the first place. So if you are fixing anchors into the soffit of a concrete bridge, you need to test 100% of those anchors to be confident that they are all working. This system is one of the cheaper systems out there. It does need a significant amount of drop points or connection points to the bridge because it can only span a small distance. It's difficult to achieve redundancy, and I'll speak about redundancy in another presentation. And it's hard to adapt it once it's been installed. It's very difficult once you have this in place in the bridge to do adaptations to it. And a lot of time with bridge maintenance, you do find at a later date when you have the platform installed that, oh, we need to access this point here instead now. So you do need to alter platforms. But it's a good, cheap, lightweight system to work with. The next area I'm going to talk about are suspended scaffolds, or more commonly known as drop scaffolds. So you can see from the image here in the bottom of the screen that you sometimes have a bridge that's got massive trusses. It's got a lot of members in it, so underdeck bracing, underdeck supports. On the wings of the structure you've also got a lot of bracing, and it's quite a congested area. So drop scaffolds are quite an obvious choice for something like this. They're a very versatile system, and they can be put into lots of different shapes and configurations. So the other two images you see on the top are the bridge with the finished platform underneath it, and then the platform on its own. You can see from the platform render that it gives you a nice working zone, but it is quite congested with members, drop members or scaffold drops. The thing with this platform system that it is labor intensive, and you do need some highly skilled scaffolders to do it. There is a large self weight to this system, and in the past, depending on the bridge capacity, I have encountered lane closures or closing of the bridge in its entirety. But And a lot of the time you can design out the need for that. There are a significant number of vertical supports required in this, and the spans on this are limited to the spans of a scaffold tube. So depending on what flooring system you use, you can get about 1.5 to 2 meters of span max. So here are some images of a finished drop scaffold underneath a major bridge. The requirement of these works was to remove walkways from the bridge, to complete repair works to these walkways and then replace them at a later date. You can see from the images there are a significant number of drop standards within it, but it does give you a nice working zone, a solid, safe working zone. And the beauty of an access platform is that if you've done your job right, people don't realize they're on a platform 100 feet above a river. It's a nice, contained, safe space. You'll see on the images here that there are lots of bracing, and we have connected to the bridge girders. So we've got girder clamps that are clamped to the bottom flange of the bridge girder in the images here on this screen. The issue with that, and we didn't have it on this project, was that if you are painting the bridge, then you've connected to a point of the bridge that you need to paint. So you will have to move that connection point at a later date. And this can be one of the challenges with drop scaffolds. So you need to come up with an alternative way to move your supports so you can paint underneath them and then replace those supports back on once the paint is has cured. So next up is space frames. So space frames are a fantastic structural element. They're essentially a 3D truss, and the ones that you see in these images here are about the size of a tennis court. Space frames are strong, they're lightweight in themselves, their strength to weight ratio is significant, and the components of it are lightweight as well, so you can build it quite easily. We do quite long spans on these. You're talking maybe 25 meters plus. They're very modular and efficient. They are very rigid when they're installed, and you do not notice the wind effects or imposed load effects. You don't notice the movement in the platform system. I've worked on a lot of space frame platform systems myself over the years, and I'm a bit of a fan of this structure. You can see from the images on the bottom the kind of layout and shape of the structure, and also you can adjust the depth of space frames. So you have a scenario on a bridge where the bridge is already in disrepair. You may be restricted to the amount of load that you can put through your cables into the bridge. So is it better for you to have a deep space frame that can span longer, but the reactions that puts into the bridge are too much? So what you can do is you can reduce the depth of the space frame, which reduces the self weight, and then you can put in load to your bridge at closer spaces, and it's a balance between what works best for the bridge and the system. I'm going to talk a bit of detail in this about two different ways you can do platforms, space frame platforms. I'm going to talk about the failure mechanisms, but that doesn't mean that they're an unsafe item. We know so much about these space frames that we know the weakest member in them, and if we make that weakest member strong enough, then they can support any load that is applied to them. You can see the image here on the top of the screen is a typical layout of a space frame platform, and this is a pinned space frame platform. So what do I mean by that? A pinned space frame platform is essentially a node and stick type system. You can see the red bits in this image are the nodes, and then they're connected by members in the horizontal, vertical and diagonal direction to other nodes. And then once you've completed that interlocking pyramid type arrangement, you board out the top with plywood. This system is a space frame that is pinned. And what I mean by that is, if we look on the image in the bottom, when you apply load to the platform between supports, you get bending in it, which results in compression in the top cord and tension in the bottom cord. So with this compression in the top cord, you also have bending in the top cord from the weight of the imposed load from the boards that are applied on it, because these top cords support the boards as well. So the failure mechanism in this, from our simply supported bending moment diagram, is a combined compression and bending failure in the top cord, which is a sudden failure, and it's something that you want to avoid if possible. You want to have a failure mechanism that gives you notice and warning of a failure that may happen. The next space frame system we're going to talk about are ductile space frames. So you can see from the image here, you've got your red members, you've got your grey nodes, and then you've got your plywood board system that's placed on the top. The difference with this system is that it's got two top cords, and one of these top cords is continuous. So if anyone is familiar with the design of continuous slabs in concrete design, you will have intermediate supports in this, And the benefit of the intermediate support is that if we look in the bottom image here, you've got bending in the space frame, which is compression in the top chord, tension in the bottom chord again. But in this scenario, because that top chord is continuous, it lifts the moment diagram. You get hogging over the intermediate supports, it reduces the sagging bending, and it means then that that top chord is not the critical or weakest member anymore. That member is now the bottom chord, which will fail in tension. And when something is failing in tension, you almost get an early warning from it. People describe it as it screams. I've never experienced it myself, but you do get early warning and you get noise from the member when it's in its failure mode, and that can be beneficial to operatives to get off the platform safely. Next item I'm going to speak about are scaffold beam grillages. They're a very versatile system. You can see from this image here that you've got a scaffold beam that spans between 2 points. The beam in question in this image is an X-beam, but other beams are available. And then these are the primary structural member. And you space these at certain centers, typically 1 to 1.5 or 2 meters along the width of the platform to make your platform layout. Then you need to brace these at 1 meter centers for restraint of the compression cord, and that gives you your grillage or box layout. Then on top of that, you install plywood or buffalo board, and then that gives you your platform layout. And the beauty of this is that it can be installed in different configurations. It can be installed to work around the shape of your piers, your bridges, or your abutments. They're all off-the-shelf components. So if you go into any major scaffold stockist, they will have these components in stock. So it limits your procurement time and gets you on site quicker. You can prefabricate these platforms. So you can prefabricate the entire thing off-site if you've a large enough truck to bring it to site, or you can bring it to site in sections and then lift it up to the underside of the bridge in separate little modules. And what that benefit of that is that it saves you time working at height on site. These can be adjusted quite easily on site. So one of the benefits of them is that if you do figure out that there's an extra element of space that you need to get to while under the bridge that is out with your working area, you can adjust these and build them in situ if required. They are heavy system, comparatively heavy when compared to some of the other systems, but they're definitely one of the more common systems on the market. So here are some images of scaffold beam grillages. On the top corner you'll see the Erskine Bridge. The beauty of this system was that we created a grillage platform about the size of a tennis court with 4 cables on it. We pulled it tight to the soffit, but we also had to deal with loading and unloading the bridge. So when you're doing concrete or steel repairs, you get a lot of residue and material that comes off of it from the cleaning process and blasting process. You can't just simply drop this into the water course anymore. You have to collect it. So when you collect that material, you're building up a lot of material on the platform. You need storage. But in this one on the Erskine Bridge, we created a rolling gantry crane that was able to go up and over onto the road level. And there's a cycling lane on the side here. So the truck was able to pull up underneath this gantry crane. The operatives on the platform were able to lift the material off the platform and onto the back of the truck, and it could go away again. And the same process happened in reverse for bringing paint and epoxy and concrete repair material to the platform. So it worked really, really well. The other image on the top is the Fort Road Bridge, and you can see the iconic Fort Rail Bridge in the background. The reason I'm showing this image is it just shows you a typical platform with 4 cables, 4 hoists, and the handrail system around it. It's nice and contained, it's neat, it's tidy, and it looks well. The image in the bottom of the platform in situ under a bridge, the reason I'm showing you that is you can see that there's a gate in one end, which is unusual to have a gate over a sudden drop in the handrail system. But on this bridge platform, the permanent gantry that was installed on the bridge was used to travel between the platform and the work site to bring operatives onto the platform. So when it did, the gantry pulled up close or tight to the suspended platform, and the operatives could walk between the two, so the levels were kept the same. The bottom corner, that multicolored platform that you see, that was a platform that was needed underneath a major bridge in Scotland. And because the soffit of the bridge was sloping, we needed to not only have our base platform, but tiered scaffold sections that matched the contour of the underside of the soffit of the bridge. And this allows the operatives to be within touching distance of the soffit of the bridge at all times. You can see a little tower off the top of this, and this was just required for emergency access if required to get off the platform. So we're going to review the accident statistics again now that we've looked at all these modern access systems and what has that done for accidents within our industry. So you can see from the coal mining that the deaths in coal mining have dropped or disappeared, but that's more for the fact that that industry in the UK has disappeared. You can see that in the bridge maintenance sector, the deaths per 100 million man hours worked have gone down from 18.5 to approximately 3. And that is an 84% reduction in deaths within the industry. So it's a fantastic achievement. And hopefully we can get that down even further over the course of the next few years with more modern access systems and more safer ways of operating. So I'd like to thank you for watching my presentation. I hope you liked it. And if you want to watch more, follow our social media channels and our YouTube channel for more presentations. Thanks for watching, and goodbye.